to your project. Specifically, we're going to be talking about defect estimation as a technique. And in fact, we'll touch on 3 different methods for estimating defects. I'm hoping that we can end this lecture a bit early today, because I think the ideas can be conveyed without a lot of time. But this is a material that's really relevant for your projects, and I'm going to try to emphasize one of these techniques as particularly attractive in the context of this class and in the context of many industrial projects, in hopes that you'll be able to, as I noted, put it into to use. So the problem of focus today concerns an issue that I suspect some of the teams are struggling with right now. You may be working with a code base that you've tested some, and you undoubtedly have in your issues tracking system some defects to be addressed. And, you know, a good testing session, a good peer review should reveal additional defects that require resolution. And you'll feel good getting those defects out of the way. But the largest set of defects that are present in many projects are those that are not recognized. They're not currently known. They're in the code base, but not discovered. And as you discover more defects, it's unquestionable that you're making progress. But there's a very real practical question for a lot of projects is, you know, how many more are there out there? How many more defects are there that we just haven't stumbled across yet? We may be finding a lot now, that's forward motion, but are there thousands of times that still there? Are we just dealing with a drop in an ocean? Or are we dealing with something where we're getting most of the major defects out? It's a very practical question, and it's one that should make a lot of the project managers here should be very familiar to you, right? Should make you really think after a deliverable. So we're going to be talking about this process of estimating the count of undiagnosed, undiscovered defects out there. The methods for estimating this are imperfect, like estimation methods across different problems. They're estimates, and they carry with them some biases and some limitations. But they can help you distinguish a case where you have few defects out there from a case where you have lots of defects out there. Okay, a lot to be discovered. And I will reward teams that go through this exercise, which is not terribly hard, and identify some estimate for the number of defects undiscovered. It's imperfect, but it will give you some understanding. So the 3 methods we're going to be discussing here are use of historic data, a technique which has been surprisingly widely applied, defect seeding, and a final technique which I would advocate for your projects of defect pooling. Okay. Each of these approaches has some shortcomings, some assumptions, some limited accuracy, and some dependencies. So the idea with historic data is a familiar one. And for those who have worked in larger companies, IBM, Microsoft, Yahoo, Google, what have you, you'll find that there's actually, for most such companies that focus on software, there's actually a large body of evidence concerning past defect densities. When I say defect densities, I'm talking about not just count of defects per project, because why wouldn't we just use count of defects per project? Why isn't that as insightful as density? So
you can extrapolate density.
Yeah. And so particularly defects per project, it can be highly variable based on the size of the project. And so you can't really take a number from one project and translate it directly into another, because the next project might be a lot smaller or might be a lot larger. What often gets more to the heart of the issue, it's more substantive measure, is the density. It's how many defects are there, say, per 1,000 lines of code. So you have 1,000 lines of Java code or JavaScript code for this application. How many defects do we get per 1,000 lines? And the idea here is, look, you know, we have many projects in this company. People shift around between projects. And roughly speaking, with similar technologies, similar personnel, similar types of code, we'd expect roughly similar density. So suppose you found a certain number of defects so far for your project. You multiply it by a ratio. The ratio of, on the one hand, the number of the density of defects that are found in other projects. Maybe it's, you know, 50 defects per 1,000 lines of code, and you divide it by the density of defects you found thus far. Maybe it's, you know, 20 defects per 1,000 lines of code. So traditionally, you have 50 per 1,000 lines of code. Here you have 20, and you multiply that times the number of defects that you've found so far, which might be, you know, 100 defects, something like that, and you'd get some estimate for the number of defects that are out there. Okay, so this would provide an estimate, say, of 250 defects. So the total number of defects out there is estimated to be this. It's reflecting the fact that you found a certain number of defects so far, and you have a certain density of found defects thus far. Okay. Another way that's much simpler to apply this, which may be obvious to some of you, is, look, you have a certain size code base, 10,000 lines of code, and there's, say, 50 defects per 1,000 lines of code. So 50 times 10 divided by the 1,000 lines of code, right? 10,000 divided by the 1,000 lines of code is 50 times 10, or 500 defects total. Okay, it's another way to do it, to estimate the total number of defects. The primary problem is multifold. Well, you tell me, what are some problems of this technique to apply for you? Or suppose you were in a small startup in town. What are some problems with it? Apply historic rates.
People working on the code has changed.
People working on the code has changed. Good. That's one thing. How about another thing which may change? Yeah.
Rushed.
Yeah, a project's in very different circumstance if it's being rushed out for a stakeholder deadline versus one that's able to be undertaken with due deliberative progress. How about other things?
Different technologies.
Yeah, different technology. I mean, technology evolves so fast in the software development area. It's mind-boggling. You know, the students who come out of this class don't really see that, but I will tell you that the technologies 5 years ago that the students in this class would be using are quite different than the technologies now. And even the technologies which are in some sense the same, you know, JavaScript, how we write JavaScript, what libraries are available, very different. You know, we didn't have Node.js back then. You know, Angular 2 wasn't around. We didn't have, you know, Mocha around as a test framework. So a lot of big differences. Ajax was a fairly new technique, the asynchronous JavaScript, etc. So technologies and their associated sort of libraries and tools evolve. How about other things? Well, the difficulty of the problem that you're addressing. This goes a little bit to the sort of the rush and the timing. I mean, there's actually different levels of difficulty of projects we take on. The projects which you folks are undertaking are quite different from 5 years ago. And I might add, quite a lot better. Why? Well, it's not that the students are that much brighter. The tools, the technologies, the libraries, the user base online to support it have all come quite a long way, actually. And this means that the projects being taken on are more aggressive. They're more intricative. They involve more pieces. There was a time, 10 years ago, I remember teaching this class. Yeah, it was about 10 years ago. The class size, we had smaller classes at that time. At that point, there were 8 students in the class. Okay. 8 students.
So one team.
One team. one team. And they had a project which, you know, I hope the quality in it would make up for the fact that it wasn't as full featured as I would have liked to have seen. So they were going to do they were doing a project for renting lockers and maintaining the library of the CSSS. Okay, so they would have this little system as a web-based system so that people could check out books and people could get lockers. Sorry?
Was this completed?
Sorta. It did not complete with, shall we say, adequate quality. So they had someone over there may mention me asking a question 2 days ago about this is great. You have all these test reports and so on. Do you actually look at the results? So they had these test reports that were consistently describing the results of their automated tests. Great. I just loved it. It was like diving into chocolate or something. It was great. But then I started reading them more carefully, the logs of their tests, you know, which they gave me to document the excellence of their testing. And test after test after test, I kept on finding the log was it was oddly similar between them. And I found out what the log was actually saying is essentially that the person came to this, they were going through a predecessor to sort of Selenium. It was pre-Selenium technologies, but it was basically driving the web browser. It may have been Water, web application testing in Ruby or something before that. Anyway, they kept on coming to the system, and the test after test after test after test all ran to completion because it was never able to log into the system. You know, so that the log just had this message. It was like, you know, login failed, login failed. And yet they put 3 thumbs up, which I guess is 2 thumbs and a toe or something. You know, 3 thumbs up, succeeded. Why? Well, it ran. You know, it didn't crash. It didn't crash because it didn't log in, buddy. You know, and yeah, their system, when you did log in, it lacked full support for the multitude of operations required to rent a locker. Or check out a book. Maybe you could check out a book, but you couldn't return it or something. Or you could get a locker, but you couldn't not get it anymore or something like that. Anyway, it lacked full features. And your systems are much better than that, but they're more complicated because of that. And so using their code base to judge your success, well, wouldn't you love that? Man, if I compare against that. That would be an easy thing, but it wouldn't be an apples to apples comparison, right? Okay, so let's talk about the next 2 techniques. The next 2 techniques are based on a simple idea, and that's why I think we should be able to finish this lecture soon. Okay. The idea here is, suppose you have a lake, you have a slough, and a big slough, and you want to estimate the total number of fish in that lake. Okay. And you have 100 fish tags. 100 tags you can sort of put onto the fins of the fish that will stick there on the fish. How could you estimate the number of fish that are in the lake? Give me a sense. What could you do to estimate the number of fish out there?
Put the tags on the fish and then come back once they've all mixed up.
Yeah.
And see the proportion of fish that have tags in their bill.
Bingo! Bingo, that's exactly it. I know, I saw some folks over there grinning impishly. They were probably thinking of throwing a hand grenade in the slough or something common like that. But no, this this is a much more effective technique, particularly if you're interested in keeping the fish alive. Yeah, no cyanide or something like that. Especially because this is going to analogize to your project, and that's not recommended. Hand grenades and cyanide are not recommended for your projects. Okay, so the basic idea here is you tag the fish, and you hopefully allow them to mix so that the fish are, all the fish you've tagged are not right next to you. And then you look at what proportion, you come back and you look at what proportion of the fish that you see have tags on them, right? So suppose that the fraction that you see, you come back later and you look at fish and you find that only a very small number of them have tags on them. What would that suggest?
There's a lot of fish.
There's a lot of fish out there. You caught the sample, but it's only a small fraction of the total sample. So if you caught 100 fish, and only 1 out of 100 of those you see has a tag on it, how many fish might you estimate there are? Yeah, 10,000. Good man. 100 times 100, right? 10 to the fourth. By contrast, suppose that a good half the fish you see have this tag on it when you come back. How many fish are there? Is it more or less than that 10,000? Yeah, a lot fewer fish. Suppose that half of them had the tag, half didn't. How many fish would you guess there are? 200. On the order. I mean, this is not perfect, right? But it gives you a sense. We're a lot more confident there's a lot more fish if we only see very few having the tag. So this is the basic idea, right? Okay, so you could do something like catch, tag, and release 50 fish. Then you catch 100 more fish. And if you find that 5 of those caught fish, 5 out of the 100, those caught the second round, are found to be tagged, then you figure, okay, this original catch of 50 fish was only 1/20th of the total. 1/20th, they got it because 5 out of this 100, that's 1/20th of that, right? So these 50 are only estimated to be 1/20th of the total population. And so we're guessing that, okay, there's 1,000 fish out there, right? Here, the basic logic is here, right? Since we caught 5 out of 50 fish with the later catch, 5 out of these originally caught 50, we estimate that's a fraction of all fish that we've caught in the later catch. So, we figure, okay, of these 100 fish we caught the second time round, we caught 1/10 of those ones we originally tagged, and therefore, there's probably 100 times 10 out there, or 1,000. Does that make sense to people? Does that make sense? That, look, if all the fish that you found, and these could be all, but if half of them, if you caught all 50 of your original fish by catching those 100, there's probably not many fish in the pond. You may have caught all of them now. These 100 may be all of them. On the other hand, if you caught these and only 1 out of your original 50 was in there, there's probably a lot out there, right? And it's probably 50 times this out there, because we'd have to have 50 catches of 100 fish to get all 50 of the ones we had originally caught. So 50 times that, right? In this case, 5 over 50 is 1/10. And so we'd estimate there's 1,000. Does this make sense, this logic? Okay, I want you to be able to apply it to your projects. Okay, I want you to be able to apply it to a final exam. Okay, now there's some assumptions here. One assumption is the catch of the fish are independent. Look, if I catch fish earlier, those 50, and I catch fish later, 100, I'm not catching just the fish that go in a certain area of it, right? Or maybe I'm catching the less elusive fish. I'm catching the fish that are the top dwellers in the pond, right? Or maybe the small fish are getting out because my net is of a certain size or something like that. So that could be challenged about, to what degree these are independent catches. There's some other considerations there too. Maybe I'm only catching from a certain region of the pond. Maybe I'm only catching the fish that are in that region. I'm not sampling fish elsewhere, right? These are rough estimates. So we have to bear these in mind. So defect seeding, both the next approaches, defect seeding, defect pooling, will be reflective of the same basic idea. So with defect seeding, the idea is, believe it or not, that there's an agreed upon plan to introduce some defects into the code base. Naturally, you record where you introduce them, right? So you introduce them into the code base. Why would you do that? Why would you introduce defects into the code base?
Using cyanide.
Well, okay, in a way, it helps you estimate the number that are out there. But in what concrete way does this help? Well, these are the tagged fish, right? And you see how many of them are what? Why would you do this? You introduce defects, and you're interested in what?
I want to see how widespread the implications of effects are.
Oh, okay. In a way, widespread for testing, right? What fraction of these defects do you actually find subsequently within a certain period of time? If you have really good testing in place, like I hope you will have for ID5, you should find a large fraction of these defects. They should pop out at you. One test case or another reveals each of them in turn, and you find them all, right? In which case, you're in a great situation. It's like you tagged all these fish, and you come and you catch 50 more fish, and they're all the same fish. Suggests there's not many fish out there, just the ones you tagged, right? If you catch all these different defects again, through your testing processes, you're doing pretty good. Your testing processes are catching a large fraction of things out there. So here we have a total number of defects we found to now. You consider, okay, how many seeded defects were found versus the total number that have been seeded. And it's just like the tag analogy, right? Just like the tag analogy. You have a certain fraction of those that you found were of those that you tagged were found, and you multiply it by the total number that you've done. It's just completely analogous to that formula we had earlier, right? We had a formula which basically specifies the same thing for fish. Okay, so same basic idea with this. Okay, and what are the caveats here? What do you have to be careful with, though, for this? What are the things you have to be careful about? Yes.
Your one bug or defect introducing may cause a number of other defects that wouldn't be there if you had introduced the initial one.
Good. Yeah, that's an excellent point. Excellent point. I really appreciate that, Nick. So there's an issue of cascading here, right? That one like the defect you introduce, for example, may block other defects. It may in fact block their being discovered. Other defects that you introduce may block the discovery of. So if you introduce defect A, it may block discovery of defect B. So they're not independent. Generally, you want seeded defects to cover broad areas of functionality, many levels of severity, and you want to seed them prior to the beginning of tests, right? So you want to institute a set of testing following this to see what's found. So you're going to have manual testers, you're going to have some exploratory testing, some manual testing that's based on clearly defined test cases, and then you have a set of automated tests, and you see which of them get found. But there is the possibility that they will interact with each other, and there is the possibility that's disconcerting. They may block discovery of other defects that are real defects. So you've lost a bit of opportunity here, right? You also want to intercept these quickly, right? You've got this defect discovery pipeline, and you don't want these to be acted on by developers to fix them, because after all, they're artificial bugs. You want to catch them at time of sanitization. What is sanitization? You're doing what with sanitization? Yeah.
You're triaging the reported bugs so that you actually see if they're actual defects or if there's something you know about it. It's part of this.
Yeah, you know about it. It's from a past version of the system. It's a duplicate of another thing.
It's part of the system. It's supposed to be.
It's part of the system. Was based on misunderstanding. So great. We distinguish it a little bit, just to clarify the terminology, we distinguish it a little bit from triage, because sanitization is about, is this a real defect? Triage is normally about how important is this, and particularly how important is it for us to fix this, okay? Do we really need to fix this? And often that involves a process called directed triage, which is, by the way, also examinable. Directed triage involves deliberately wading through the sanitized bug reports, already sanitized, to identify those, to try to figure out what severity are there, what priority, how are we doing, right? This is something like project managers may want to do. Like, what defects are out there? Like, how serious are these things? Are they going to make us look bad on the demo? Are we ready for a stakeholder meeting? Are we ready for the deliverable? Which of these defects do we actually want to fix? And which do we not want to fix? Because there's not time to test it after fixing it, and it could introduce a worse problem. So triage is a little bit different from sanitization, but the way you were using it, yeah, you described exactly the right process. Exactly the right. So you want to intercept quickly, and it can hide other problems, and it can cause resentment. Right? Someone's code was working pretty. They really sweated over this algorithm. They put their all into it. They're feeling really good about it, and suddenly there's a defect that shows up in the defect reports. This algorithm is broken, and it doesn't make them feel great. You stuck a bug into my algorithm. What are we trying to do here, right? So you also want to keep these simple, like change 1 or 2 lines of code. And obviously, it goes without saying, you want to eliminate these carefully before you ship, right? You don't want a defect going in there. Now, defect pooling is the highly actionable technique that I really want you folks to do. It's beautiful, and you can do it really easily, and it can allow you to get estimates and avoid the challenges associated with defect seeding. So the idea here is, look, you hold the bug party. But in fact, what you really hold is 2 bug parties. Maybe you can start to see where I'm going with this. One that's operating in one area of Sphinx and one in another area of Sphinx, or something like that. One of these teams, so the 2 teams operate, and this is key, they operate independently. Why is it going to be important that they operate independently?
Because if a person knows about some bugs, they're either more inclined to go and look at those and report them, or ignore those for other.
Or ignore them. So it could really skew the results in terms of how many they have in common, which is going to be absolutely central. Just like it was central to say, we go and have a second round of fishing and we see how many tags there are. It's the number that are in common, that are tagged, that we got the second time. That's absolutely key here. So you're interested in how many defects did group A find? How many defects did group B find? And then how many did they find in common? So suppose they found a lot in common. What would that suggest about the number of defects out there? Suppose 90% of those, suppose they found 400 defects, but 90% of them were in common with the other team, which found a roughly similar number. Maybe it found 350. If 90% of those were in common, what would it suggest?
Smaller number discovered.
Yeah, this is comparatively small number undiscovered. Look, there's hundreds of defects. Maybe it's around, somewhere upwards of 400. But it's not like there's tens of thousands of defects out there. By contrast, suppose this one discovers 400 and this 350, and suppose there's only 1% overlap. What would that suggest?
A big number of undiscovered.
Big number of undiscovered defects. Yeah, they're finding hundreds of defects, but that's just a drop in the bucket compared to what's out there. There's just lots more like them. They're finding different sets. Okay, so same basic mathematics, right? So you establish two different independent pools of found defects. These are different teams, different subsets of your team, operating the same day without messaging each other and for roughly the same amounts of time and testing the full scope of the software. You do not want one group testing one part of the system and the other group testing the other not. Why not? Yeah.
Also limits the number of bugs.
Yeah, exactly. The whole thing is they're basically doing comparable testing, and what number do they find in common compared to the total number they find. So you don't want it to limit it to just you know, a certain area of the software. In both cases, they're using kind of comparable levels of functionality testing the different components, right? So you have defects, you have pools created for different sets of staff. You have different people go to different places, ideally work at the same time, same version of the software, et cetera. And the alternative is you could have, you know, the other team work at a slightly later time, like the next day, as long as there's no communication. It's not so good to have the same people do it the next day because they'll remember. They'll say, oh, you know, we found lots in that area. Let's go after that again. Or, you know, we're not going to do this again, you know, and heading off. Just like Nick said, it's not obvious. At the least, you know, they won't, if they share information, it's not going to leave it unbiased. They're either going to try to find the same defects or try to avoid the same defects, one way or the other. So the estimation formula is basically the same deal as before, okay? And it can be boiled down to defects in pool A times defects in pool B divided by defects in both pools. So suppose you have pool A here, you're going to multiply it by 350 divided by 150, okay? So this is just some fraction of this whole, and you're going to multiply the 400 by that, by 1 over that fraction. Or same mathematics, 350 times 400 divided by 150. The key is you've got the defects in one pool times the defects in the other divided by the defects in both pools. Make sense? So this should be something you should do. I mean, you should all be having bug parties for the next deliverable for sure. And you should be able to estimate from this the number of undiagnosed defects. In fact, it might be a service to others. It would be a service to others when you're testing their software if you do the same thing for them. Test it in subgroups. Half your team on one place, half the team the other, and you see, and you can give a total estimate for the number of defects out there in their software. Yeah, it'd be good. Okay, so what's the problem here? Well, there's a certain amount of overhead. Yeah, you could say there's a certain amount of waste because they're discovering the same defects again. But that's exactly how we get insights into how many undiagnosed defects out there, right? Here it'll be very important to record the defects, to record, you know, what defects you found, and to do so with enough detail that you know is basically the same issue. What you enter is probably going to be different when, you know, we enter into the details of the software, but basically it's the same thing you saw. You just entered different names and it gave the same basic error message. Does that make sense? Okay. Okay. Now, simple strategy, actionable. I'd encourage you to act on it before the next deliverable. Okay? Okay. So that's about finding undiagnosed defects. I contemplated having another lecture here on testing object-oriented software, because there's some special considerations with that. And I thought, well, if I do it in a brief time, I could do it justice. But then I thought, you know, we're short of pop quizzes. Yeah, it's about time, folks. So put away your stuff. Now, that's the bad news. The good news is that one of the questions on this pop quiz is about how you estimate the number of undiagnosed defects out there. So if you are paying attention, you will do well between that and your name, right? Okay. Here we go. And when you finish, you may leave the classroom, okay? And we'll discuss the answers next one. There's got to be a better way to parallelize this. Now, I decided we'd do this a little bit on the earlier side so that we could have least chance of running into the next class here, okay? So you've got a good almost half hour with this to fill it out. And hopefully don't just stare at it. Okay. You know, the older I get, the more I understood when my teachers licked their fingers. And they could have and I never quite got into that habit. Yeah, yeah. We've been having some attendance issues, and I reward showing up because it matters to your team. Is there anyone who hasn't received one here other than this last round? Oh, I should probably stop recording. Okay. Any questions, just ask.